Hi, my name is Langston Wilcox, and today I'll be presenting my experiment on circuit analysis. Here's a brief introduction of our lab. The purpose of this lab was to predict and measure the behavior of circuits using energy and current conservation principles, test Ohm's law, and examine resistors and capacitors. For our results preview, the DC current was about 25 to 28 milliamps. The RC time constants were, for the 10 ohm bulb, about 50 seconds, and for the 20 ohm bulb, about 10 seconds. We used three fundamental principles: Ohm's law, voltage is directly proportional to current; no rule, current entering a junction equals current leaving; and loop rule, the sum of voltages in a closed loop must be zero. And now I'm going to move on to the first circuit, the DC circuit. We built the circuit using a system of two 1.5 volt batteries, 47 ohm and 100 ohm resistors, two ammeters, wires, and a voltmeter, while our surroundings were the lab room. We assumed the electric field in the connecting wires was negligible. Some key steps of our procedure include assembling the circuit and recording current and voltage, reversing an ammeter and noting the changes, adding a voltmeter and observing effects, and measuring potential differences across components. We predicted 20 milliamps but measured 14 milliamps, and reversing the ammeter gave 12 milliamps. Adding a voltmeter in series caused 0 amps, showing that the voltmeter likely should have been placed in parallel. The potential difference measurements confirmed our theoretical values. The 47 ohm resistor was -1 volt, the 100 ohm resistor was -2 volts, and the total voltage was 3 volts. Here's the rest of our graph, which shows a steady yet not uniform decrease in voltage as resistance increases. Reconnecting the voltmeter resulted in 10 milliamps. Replacing the voltmeter with another ammeter increased the current to 50 milliamps due to lower total resistance. The resistance values of the components were close but not the same as the expected values. And now I'm going to move on to the second circuit, the RC circuit. The system of the circuit was two 1.5 volt batteries, one capacitor, one 10 ohm bulb, and one 20 ohm bulb. The surroundings were the lab room once again. We tested a capacitor circuit with a 1F capacitor, 10 ohm bulb, and 20 ohm bulb to observe charging and discharging behavior. We timed brightness changes with a stopwatch. The results were the 10 ohm bulb was charging for 60 seconds and discharging for 42 seconds. The 20 ohm bulb was charging for 12 seconds and discharging for 10.5 seconds. The first capacitor seemed to be fully charged as it took approximately 50 seconds, whereas the second capacitor seemed to not be charged as it took approximately 10 seconds when it should have taken 100. Here's our graph that shows that the voltage decreased over time. Errors in our results possibly came from human errors, including setup mistakes or calculation errors, material issues, including aging batteries, uncharged capacitors, faulty meters, or faulty bulbs. My answers to the what if question are that in an ideal model, charging would be fairly instant. However, real-world resistance would slow it down. Our ammeter showed a 2-second delay, proving resistance affects capacitor charging. The times were different due to the minimal amounts of resistance in each component. To summarize, measured values were close to predictions but impacted by real-world resistance. Resistors and capacitors followed expected behaviors, and the meter placement significantly affected the rating.